I love a good code simulation. And today we're going to look at a sim that's actually a combination of two smaller styles of simulation, stacked on top of each other: an agent or particle simulation, and a grid or a field simulation. Let's deconstruct a slime mold sim that I put together in a Godot Compute Shader. We'll take it apart and figure out how it works under the hood. The simulation we're looking at is heavily based on Jeff Jones's 2010 paper, Characteristics of Pattern Formation and Evolution in Approximations of Fusarium Transport Networks. Whew, that's a mouthful. But I've also taken inspiration from others like Jensen and Sebastian Legge. It's a computational model inspired by our observations of slime molds in the real world, not a true biological simulation. Unlike some of the other sims I've done on the channel, where particles interact directly with one another, these slime mold agents work differently by interacting through their environment and don't really sense each other directly. So in this model, each particle can only do a few things. It can move forward, it can sense a chemical trail, it can decide to turn left or right or keep going straight before moving, and it leaves behind some chemicals in the trail after it moves. And for the chemical trails, the model stores the concentration of the chemicals in a grid or a field. The chemicals in each grid cell will spread out and evaporate over time. The combination of these two sets of roles creates a feedback loop, where the particles and the field influence each other, giving us the neat emergent designs. Later in this video, we'll focus more on the structure of the compute shader. But for now, let's just try to understand the two individual parts of the bigger picture, and how we'll handle them in Godot. To start, we're going to ignore the chemical trail part of the simulation. In this sim, we have a list of particles. Each particle has both a location in space and a heading where it's pointing. For every frame in the sim, the particles want to move forward by some amount. But before they move, they need to make a decision of which way to turn. They could make this choice by any number of ways, like sensing chemicals around them. But for now, we'll just assume they randomly choose left, right, or keep going straight. Once they determine which way they want to go, they update their own heading direction, and then finish up by moving forward. And that's basically it. Just loop over thousands of particles every frame and have them do that. It's kind of bare minimum and it's pretty random, but it is the simplest way to understand what the particles are actually doing each tick. To speed up this loop, we're running the sim in a GLSL compute shader using Godot's rendering server. So we'll be able to run the particle logic in parallel batches on our GPU. Inside the compute shader, we'll store the list of particles in a GPU texture, where each pixel in the image stores a single particle's data. We'll see more technical details later, and you can check out our video on how to use data textures for more bits on that concept. Okay, that's it for the first sim. Now let's ignore the particle sim for a moment. In the second sim, we'll be keeping track of a grid of values. This grid could be used to represent anything, but for our case, we'll be simulating a trail of chemical pheromones in our grid. Each grid cell can have any amount of pheromone. There are really only two steps to this sim: diffusion and evaporation. For every step in the sim, the pheromones slowly spread out into neighboring grid cells using a diffusion process. But over time, that diffusion would cause all of the pheromone to just be equally spread out across the world space. So to keep things moving, while the grid is diffusing, some of the pheromone is removed from each grid cell using evaporation. And that's basically it for the second sim. We'll run a simple diffusion and evaporation process on each of the pixels in the grid. Like the first sim, it's kind of basic, and by itself usually ends in boring or empty fields given enough time. We'll use the same compute shader as before so we can process all of the pixels in parallel groups on the GPU. Inside the compute shader, we'll store the entire pheromone field in a single GPU texture, where each pixel stores how much pheromone it has. Now let's bring the two sims together. By themselves, each mini simulation is kind of boring, but now we'll introduce a feedback loop. To do this, we're going to change two things to the particle side. First, each particle will read from the pheromone field by using a sensing function. Instead of choosing a random direction like before, now the agent can determine if it should go left or right or continue straight, depending on the results that it finds in the chemical trail. And second, the particles will deposit some new pheromone into the field at the end of each frame. There are a bunch of ways we can handle the trail sensing logic, but to keep it as close to the original algorithm as possible, let's use 3 sensors. It works like this. Each particle will look straight ahead a certain distance, and also look to the left and to the right a certain number of degrees. Now, with those 3 values, the particle can choose to move towards the highest concentration. To add a little bit more flair, we make the particles sometimes choose randomly to keep things stochastic. So now each particle will either keep pointing straight, or it will turn left a certain amount, or turn right by that same amount. After they actually change direction, or not, the particle moves forward just like it did before. Before the frame is finished, the particle should be in its new location, and that's where the particle will deposit some amount of chemical back into the trail texture for the next frame. Nice. This creates the feedback loop between the sims, and so the emergent slime mold behaviors appear. The particles are adding to the trail every frame, and as the trail diffuses and evaporates, the agents will make different decisions based on what they're sensing. Most of the settings for the 2 simulations can be adjusted in real time with sliders and drop-downs to get some crazy results. Let's take a look at the settings real quick. The parameters are broken down into 3 categories. The first category controls the overall simulation, and lets us control basic stuff like how many particles we'll have, the color scheme for the drawing, and the speed of the simulation. You can choose the number of particles from this list. The color scheme selector here uses a gradient color resource to change the way the field values are drawn to screen. There are over 20 different color schemes to choose from. I have another video coming soon where I'll be going over that gradient technique in more detail. And here, the simulation speed slider controls both the speed of the particles and the speed of the diffusion and decay process. The second category of parameters controls the behavior of the particles. We can adjust the move distance, configure the sensor distance and their angles, control how much a particle will turn, throw in some randomness, and set how much pheromone a particle will deposit each frame. The last category controls the diffusion and evaporation processes, letting us control how long the trails last and spread out. I found myself just trying different values and being amazed at some of the visuals it made. Here are a few of my favorites. Now let's get into the technical dessert. If you're interested in compute shaders, there are a bunch of videos on the channel where I implement all sorts of simulations using these techniques with Godot's rendering server. Check out our playlist for those deep dives. You can also find the code for the slime mold project and most of our other projects on our GitHub page. So here's how we'll do it. As you can see in this diagram, the compute shader runs in 2 passes every frame. The first pass loops over every particle, having each particle sense their environment, turn and move into new positions, and deposit the chemical back into the trail. The second pass processes the entire trail field texture, pixel by pixel in batches. It first spreads out the field using the neighborhood diffusion blur, then follows up with the evaporation process. The list of particles for the first pass will be sent into the shader using a 2D texture. Each pixel in this texture represents a single particle, but we generally won't use all of these pixels. Each pixel has a red, green, and blue channel. We'll store the particle's X and Y position in the red and green channels, and we'll store the particle's heading in the blue channel. The chemical trail for pass 2 will be sent to the shader as another 2D texture. In this texture, each pixel represents a grid cell in space, and really only needs to contain a single channel to store the amount of pheromone in that cell. We could use just the red channel for that value, but I went ahead and placed the single value into all 3 channels, so we get a nice grayscale field when we draw it to screen. Those 2 textures contain all of the data we need to run both pieces of the simulation. However, because we're reading from and writing to these textures, we can't use the same texture for both operations. So we're going to create duplicate textures. There will actually be 4 textures in total, 2 for the particles and 2 for the trail field. During each frame, one set of these textures will be used as the inputs, and that means the second set of textures will act as the outputs. We'll use a technique called double buffering to ping-pong the input and output textures back and forth. At the start of every frame, we'll swap which textures are bound for input and output, using the concept of uniform sets. This is pretty handy because it means we never need to copy the simulation data back down to the CPU every frame. And it avoids the problems that would happen if we tried to read from and write to the same texture at the same time. To quickly draw the results on screen, we'll use a concept called texture 2DRD. Again, I have videos on the channel that cover this technique in more detail, but for now you can think of this as a label or a name tag that points to the image. Instead of reading the results from the GPU back to the CPU every frame, just so we can draw it, the texture 2DRD lets Godot render the textures directly from the GPU. This was one of those techniques that improved performance so much in our projects that now we use it for almost everything. The other important concept in this shader is choosing the correct dispatch size for each simulation pass. For the particle simulation in the first pass, we'll use the dimensions of the compute texture to determine how many parallel workgroups to run on the GPU. Then similarly, for the trail simulation in the second pass, we'll use the trail texture's width and height to calculate its dispatch size. With those textures in place, we can run both passes each frame and swap the buffers for the next iteration. As far as performance is concerned, we just need to be careful of two things. First, how many particles do we want for the particle simulation? Our compute texture is 256 by 256, so technically we could have just over 65,000 particles in it, even though we won't use them all. Second, how many pixels are in the trail texture used in the trail simulation? Right now, we're storing the trail in a 512 by 512 texture, so the diffusion and decay logic will need to run once for each of the 262,000 pixels every frame. We could always make the trail texture bigger if we want more detail, but it's worth remembering that every increase means more cells need to be processed on the GPU every frame. And there we go, a fully functioning compute shader that runs two distinct simulations each frame. Nice. Slime molds are a fun little combination of two different sub-simulations. They use two different styles of processing, both particle-based and field-based, that feed into each other. You can find this combined model in some of our other simulations too, for example in our particle linear and upcoming ant colonies topics. If you know of other sims that combine these techniques, let me know in the comments. You can find the slime mold project on our GitHub page. It's open source, so feel free to experiment with it and make your own improvements. Hopefully you found this video helpful, and maybe learned a few things about Godot's compute shaders and combining different styles of simulations together. If you have questions or comments, you know where to find me. Thanks for watching the Pathfinder's Codex, and as usual, never stop trying new things.